Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. Today we're going to be speaking with Vincent Pluvinage, CEO of 1D Battery Sciences. Vincent was a wealth of knowledge and a great help when I was working on Tesla Silicon for the Tesla Battery Day series. 1D is now coming out of stealth mode, and I thought it would be a good time to have Vincent on the channel to pick his brain. Let's get right into it. The best place to start here is what your product is and the technology that it uses. Could you walk us through the specific way that 1D is using silicon? It was of particular interest to me because it was different from other technologies that I've seen on the market.
Yeah, so to begin with, we are not a material supplier, and that surprises many people. But our product, if you wish, is actually a manufacturing process. And we call that the Sinanode step. And let me explain why. The process actually takes commercial graphite, which can come from multiple suppliers, and it's already qualified by EV cell makers, and it's produced in various places around the world in very large quantities and purchased at very low cost already. And then we add value to that graphite by processing it in such a way that we grow little hair of silicon onto the graphite particles. So essentially the graphite comes in the normal way, already qualified, and without any further modification, the process grows silicon hair, tiny little hair, onto each particle. There may be as much as 100 to 200,000 hair on each particles of graphite. And when you finish with that, it looks like graphite, it behaves like graphite. However, its capacity is 3 times that of the original graphite you started with.
And I'd like to emphasize the significance of what you're saying here, because what 1D is not trying to do is trying to replace other suppliers in the supply chain. What it's doing is it's piggybacking on top of the existing supply chain. And when a company starts a gigafactory, they usually line up those material suppliers years in advance, and those are pretty much locked in. And it's hard to break into that supply chain.
That's exactly right. I like to joke that we are the disruptor that does not disrupt. And the reason is very simple, right? If you look at the OEMs, which are the ultimate customers, they are very, very large companies. They have a global footprint. They sell millions and millions of cars. And today they are scrambling because there is 4 key challenges. First, of course, they need innovation because every OEM knows that they need to increase the range, the charging speed, and decrease the cost. And all of that requires innovations. But in addition to that, they need huge amount of materials and huge amount of factory capacity. They need suppliers that they can rely on, and they need to deal with cost in a way that makes them able to compete. The vast majority of the cars sold today sell for less than $30,000 per car. And the batteries is what makes EVs too expensive. So unless you can offer enough range and with a reasonable battery that is below that inexpensive cars, you won't be able to compete. So if you look at that, what are they doing? Well, they're doing 3 things. They're securing key technologies. They're vertically integrating so that they can actually become themselves more of an EV cell maker while leveraging others, including other cell makers. And then they're also following what I call a localization strategy, which is that they need in each key market to be able to rely on localized supply for the materials and the cells, because moving things around in huge quantities is just too expensive. And so once you realize that, it's pretty obvious that the only way that a new technology, especially from a small startup, could be adopted is if it tries to fit within the existing supply chain of the OEMs and fit within the existing investment that they've been making and that their suppliers have been making. So from the beginning, when I met our CTO, Yimin Ju, I was struck when I met him the first time, and I spent a year talking to him before investing, I was struck by three things. One, Yimin Zhu had an amazing way to look at the basic scientific fact, whether it's physics or chemistry, and explain it to me where I was pretty naive at the time about batteries. He had a very clear view about manufacturing and scalability, which is very rare for somebody that's good in science in the lab. Most people in the lab don't know about manufacturing. He understood the future challenges that going into large-scale manufacturing entail. And then the third part, his mindset, was always, how can I simplify and how can I reduce costs and how can I increase yield? And I knew about yield from my own personal professional experience, that if you don't have very high yield and low cost, it doesn't matter how beautiful the solution is, it will never be adopted at large scale. Because at the end of the day, it's all about economics. And so that's basically, 8 years ago is the reason that I trusted Yimin Zhu, and that me and my investors have been investing in his work and enabling this to come to market.
Well, it comes through in your approach and it comes through in the marketing, because a lot of companies, they'll lead with dazzling figures, but from the very beginning of this interview, your focus is on how can we insert ourselves into the existing ecosystem so people actually buy the product. With dozens of silicon anode products on the market, how can you differentiate yourself? Well, you can differentiate yourself by making it easier for suppliers to pick up your product. And on that note, it sounds like what you've created is actually a drop-in solution. A lot of companies will talk about drop-in solutions, but it still requires replacing machinery, tweaking things, building a new plant with new machinery. But you're actually, could you provide your thoughts on that?
Yeah, actually, this is, I'm so glad you asked this question, Jordan, because the word drop-in has been overused and misinterpreted. And I think there is technical drop-in and business drop-in.
Now I'm going to need to jump in here because during this part of the conversation, the Zoom call kept dropping out. A business and technical drop-in are exactly what they sound like. Does this product drop right in from both a business perspective and a technical perspective? Usually when people think of a drop-in solution, they're thinking of the technical drop-in. But the business side is where things get interesting, and that's often what's neglected. A business drop-in is when it fits with the product roadmap, there's no single supplier issues, and you can leverage existing suppliers. After the Zoom call, Vincent sent me what you see on screen, which gives full detail on what he meant by a business and technical drop-in. Now let's pick back up where we're digging deep on one of the technical specifications for anode material.
An anode material must meet the EV factory acceptance criteria, which is low impurities, low batch-to-batch variation, a known BET that is acceptable, etc., which are already in use by tier 1 EV factories.
What's a BET?
BET is a way to measure the surface area of a powder. And so, for example, a good graphite, synthetic graphite, may have 2 or 3 or 4 square meter per gram.
So I'm going to connect we're talking about BET, which is surface area. Now, yeah. The reason why surface area matters for the people who don't have a battery background is the more surface area you have, the more reactive surface there is with the electrolyte. And the first few times you cycle a battery, what that does is it sucks lithium out of the electrolyte. So the less surface area that you can have, the better. One more interruption here due to Zoom difficulties. At this point, I asked Vincent what are the ways in which silicon manufacturers typically deal with the surface area problem.
So one is to keep the silicon in micron-sized particles, and then use, for example, carbon coating together with oxygen to try to hold together the silicon, and that has a lot of its own drawback. The other way people have been trying to do this is to make nano-sized silicon hidden, for example, encapsulated into an amorphous carbon matrix. And by that, you hide the silicon inside so it doesn't get into contact with the electrolyte, but you have to leave enough room for the silicon to expand and contract. These companies are trying to be graphite replacement, which means that they're competing with the graphite suppliers, which are the very people you don't want to compete with because they are already making hundreds of $millions of investment to produce hundreds of thousands of tons each of synthetic or natural graphite, which are extremely specialized type of investment. It's not something for the faint of heart. And it takes actually years to be qualified by the EV cell factories. So trying to replace that supply chain, to me, is both technically and business-wise foolish.
Exactly, because you wouldn't be able to go in, it would be very difficult to crack into an existing factory. You'd have to get into a factory that isn't built yet, and then you have to prove that your product is more reliable than better than their existing materials. So,
well, there is also an issue of cost, is that you only reduce cost by scaling up. And these guys have already scaled up. And so every time you double the volume cumulatively, you decrease cost by about 20%. They've been at it for 5 or 10 years. So to try to compete is like catching a falling knife. Yeah, they continue to decrease the cost because they continue to increase volume, and you never have the volume. Let me give you an example that people don't realize. They say, I'm first going to introduce my solution in watches, and then I'm going to go to phones, and then eventually in EVs. Well, the problem is that the most successful watch in the world is the iWatch from Apple. And they sell about 35 million a year, okay? But that's, if you think about what the batteries of 3 million cars is, it's the same as 10,000 times more than all of the iWatch. And then they say, well, the iPhone is a large market. So yes, there is 230 million iPhones sold per year. But 3 million cars is 100 times more than all of the iPhones sold per year. So there is orders of magnitude delta. And the specs are different because, it's a different cathode. It's typically LCO cathode. So you can never get down the learning curve by focusing on those markets and then hoping to catch up with the EV market.
brilliant. That's really well put. Yeah, if it's 10,000 times difference, that's 4 orders of magnitude, which is just two completely different markets. And as you said, 2 different use cases. And now that we've talked about surface area a little bit and the way other people solve that issue, how does 1D material and Sinanode, your silicon product, solve that problem?
So I'm going to give you a little demonstration. And for that demonstration here, I have a bunch of spaghetti, okay?
All right.
And so this is a typical Italian spaghetti number 3, and I hold one in my hand right there. Now imagine that this spaghetti is silicon, okay? So first of all, what you notice is that there is a very small radius and a very long length. Now this is interesting because in the case of Sinanode, the radius is about 40 nanometers. So it's definitely small enough that 2 things are true. One is the lithium ions that are floating in the electrolyte have a very small distance to get from the surface to the middle, right? Mm-hmm. And they can enter anywhere along the length, but the pathway is very, very short, much shorter than the pathway, for example, from the surface of a graphite particle to the center of the graphite particle, which is typically 5,000 nanometers or 10,000 nanometers, okay? The other thing that I want you to see is the length is so long, and that has 2 interesting properties. The first one is that it has a much smaller surface area than the equivalent number of silicon nanoparticles. And I'm going to prove it to you right now and right here, okay? So if you take this spaghetti, the surface area is the area along the length, plus the area at the bottom and the area at the top. You agree with me?
Yep.
Now I'm going to cut it in two. I have not changed the amount of silicon. It's still the same. But I've added now too little surface area at the top. And now I'm going to cut it again. And now I have four little pieces. It's still the same amount of silicon, but I've increased the surface area further. As you continue this process, you get to a bunch of tiny little particles, which have the same diameter as my nanowire, but a lot greater surface area, by about 2 orders of magnitude. As a matter of fact, the crazy part about our Sinanode process that people are completely baffled, they take a commercial graphite that has a surface area of, for example, 4 square meters per gram. They give it to us. We put it through our process and we give it back to them. And we say there is now 21% silicon nanowires on all the graphite particles. 21%. So if you start with, let's say, 100 kilograms, you now have 121 kilograms, okay? And then we say, please measure the BET surface area. And they know they started with a graphite that had 4 square meters per gram. And they know we added all of those nanowires that have nano dimensions. And so their expectation is that the surface area is huge, because if you compute the number of nanowires, we just added about, in 1 kilogram, we added about 100 million billions, 100 trillion nanowires. And we do that very quick. And they all this thin. And they measure the BET, and it's 2.8 square meters per gram. You say, how can that be? You add nanosilicon, and you end up with a lower surface area. And that's the magic of the shape. That's why shape matters. And then I'm going to make a third explanation. But before I do that, I'll let you ask a question.
Oh, I have lots of questions. That was really good. You need a science show, Vincent.
Well, let me show you something, okay? The last point is the following. What I have here is a nanowire. Now, it's a little bit bigger than a nanowire because otherwise you will not see it, okay? And I put at the top a special piece of silicon, which is called an LED, light emitting diode, okay? Now, imagine here that this is the surface of a graphite particle. Can you see that?
Yes.
Okay. And so what I'm doing is that I'm going to plug the nanowires into the graphite particle. Okay. You see what happened? The electrons flow from the graphite into the nanowires all the way to the tip. And if I move a little bit, it stops. So you can tell that the important point is that there is a connection here between the silicon and the graphite. Now, the beauty about our process is that we attach the nanowires to the graphite directly into the graphene layer at the surface of the graphite particles. And that attachment is both mechanically and electrically permanent. And it doesn't use any polymers. So why is that so important? Because in order to store lithium into my nanowire, I need not only the lithium ion to come from the electrolyte, but for each lithium ion, I need an electron to come in. And the graphite is essentially the supplier of the electrons. And the attachment point is the plug. So if you want to light up something, you take the extension cord, which is the silicon nanowires, and you plug it. And when you plug it, you end up with electrons flowing through. And so the electrons can flow very easily because after formation, the silicon nanowires is like a dry spaghetti, except that when you put a dry spaghetti in hot water, two things happen. It becomes a little thicker because the water gets into the spaghetti, and the spaghetti gets very flexible. Well, the same thing happens with nanowires. When it gets lithiated, it becomes flexible, but it remains attached. And what happens is that the mobility of electrons in lithiated nanowires is excellent. It's actually faster than the mobility of electron in graphite. So the silicon becomes amorphous, and you have very fast charging speed because electrons move very quickly on the length of the nanowire during charging, and a lot of power because electrons move out very quickly during discharging. So you not only increase charging speed, you increase power density.
Nice. And I probably the best place to go with this next is, when I first heard about your product, my gut reaction was like, oh, silicon nanowires. Typically, silicon nanowires and other implementations I've seen are very expensive. Typically, what they're doing is they're taking a metal foil and they're using silane gas or silane gas and putting a coating on it, which has quite a few issues. How are you able to manufacture this cheaply, or what?
First of all, I love this question, Jordan, because 100% of our customers start by assuming that this costs thousands of dollars per kilogram, best case. And so the biggest misconception is that this is actually cheaper than graphite. And let me explain how. First, I'm going to start with the answer, and then I'm going to tell you how we got there. If you take graphite today and you buy it in large quantities, let's assume you buy 10,000 tons of synthetic graphite EV grade. It's going to cost you probably about $8 per kilogram. Okay? Now that works out to about $6.2 per kilowatt hours for the anode material. I'm using the operating voltage of 3.62. So graphite is $6.2 per kilowatt hours. Now I take the very same graphite, no change, from the same supplier, and I add 20% nanowires onto it. What happened is that the graphite continues to serve to store the lithium back and forth. But the 20% weight of silicon can charge a lot more lithium. So the 20% of silicon can charge to 3,500 milliamperes per gram. What happened is that the combination, the composite of the graphite plus the 20% silicon nanowires has a reversible capacity around 1,000 milliamperes per gram. So you have triple the energy, the specific capacity of the graphite. And that basically decreased by about half the cost. So you end up with about the cost about $3.4 per kilowatt hours. Now there is another additional benefit if you were using silicon oxide. When you mix silicon oxide with the graphite, you end up with two problems. The first problem is not all the silicon atoms are available to alloy with the lithium, because a bunch of the bonds are occupied by the oxygen. That means that if you look at the maximum amount of lithiation, you don't get the full amount of silicon used. The second problem is when you put that into the battery, you end up with a greater loss on the first cycle. So first cycle loss is maybe 12%, whereas for graphite, it may be 6%. That means you need to supply more lithium with an oversized cathode. But the cathode material costs a lot more money. So that costs you an arm and a leg, because you have to make up for the higher loss due to the silicon by more cathode material. When we do the composite, and we start with a graphite that maybe has 94% ICE, initial colloidal efficiency, and we add 20% silicon or whatever, we then blend that and make an anode. The cycle loss is the same as with graphite. So that's the answer. Now, how do we get there? I can explain to you in a minute.
All right, I'm just gonna paraphrase what basically give people an idea of what was said there. That typically the type of silicon that, for instance, Tesla puts its batteries, it's 2 steps forward and 1 step backward. Yes, you're putting in a material that has higher energy density, but it's so poorly constructed that you lose a lot of that energy density that you've put in, and you have to make up for that by putting extra lithium in at the cathode, and the cathode is the most expensive part of the battery. And with your product, It's basically there is no two steps forward and one step backward. It's two steps forward, and you get to keep those two steps.
That's right. Now, how do we get there? And there is really three reasons. The first reason, which took many years for Yimin to develop, is in the past, 10 years ago, he was using a gold catalyst to grow the nanowire. Gold ain't cheap. But then he switched to a copper catalyst. And not only it dropped the cost dramatically, but it increased performance dramatically. And so we spent the last between, let's say, 2013 and 2018, perfecting the large-scale process using copper catalyst. Now, a catalyst, why is that so important? First, you need a cheap catalyst. Second, you need to make it in very large quantities where all the copper oxide nanoparticles are the same size, because that's what's going to determine the diameter of the nanowires. And we can do that at room temperature in a continuous process that is extremely cheap. But then when you mix it with graphite, the catalysts end up on the graphite particles, okay? And what happened when you put it in the processing tube to react with silane, 99.9% of the silane is transformed from the silane gas into silicon nanowires. There is virtually no traces of silane on the exhaust. So you don't want to waste silane. You want to use all of it to make the nanowires because that's the only thing that counts at the end, okay? So that's the first part of it.
So does the copper help pull the gas and attach it to the...
Yeah, what happened is that the following is that the little particles of copper basically at a given temperature and pressure decompose SiH4 into solid silicon and exhaust hydrogen, which we can actually reuse, okay? And the silicon itself is then solid silicon, and it grows like layer by layer. And so you start with the copper on top of the silicon, on top of the graphite, and then like a little hat, as the nanowire grows, the copper ends up in the tip, but it's copper silicide, and it's covered by silicium, and so it doesn't react with the electrolyte. It's not an impurity, and the level is like ppm level.
So the copper is basically like a seed particle then, is that
exactly? It's a seed. It's a perfect one. And what it does, it's lower the temperature so that we use less electricity, and it increases the yield so that 99.9% of the silane becomes solid, silicon nanowires. So we have no waste. But then the third piece is that in order to do the reaction, our CTO, Yimin Zhu, got rid of all the fancy gases that are expensive and dangerous. And the only other gas we use is nitrogen, which can be extracted at the manufacturing sites from the atmosphere. Nitrogen is all around us, okay? So with a modest amount of electricity, nitrogen and silane, and I'll get back to the silane in a minute, and only graphite, that's it. That's 95% of the cost. Now, the other two pieces that are important is that the cheaper the graphite, the cheaper Sinanode, because we don't buy the graphite. Okay, that's the first piece. So if our customer finds a cheaper source of graphite or wants to blend natural graphite and synthetic graphite, we can grow nanowires on any kind of graphite, including natural graphite. So they have more flexibility, and most of them end up blending the different graphite from different suppliers anyhow. Now, the other piece is, how do we do the processing? And here's the beauty about it. First, the silane we use has 5N purity, so we don't need to remove any impurities. It's also already pure enough. And it's made from MGS, metallurgical grade silicon, in very large distillation columns. And these silanes are very inexpensive because they are used to make solar cells. And as you know, solar cells are made in huge quantities at very low price. So we use a precursor that is not the silane that you use in, for example, semiconductor foundries, which is expensive. We use a silane that is used, for example, for solar cell manufacturing. So that silane is less expensive, and it's available in huge quantities. It's available in quantities today that is sufficient to do 30 million cars, okay? And now, with the second piece of Yimin's genius is, how do I reduce the risk of CapEx? Most people, when they scale up, they have to invent new machines, and they have to test new machines, And the machines are expensive because they're brand new. What he took CVD equipment, chemical vapor deposition equipment, that is used today by the solar cell industry. And normally you put in the tube some wafers, and then you close the tube, you heat it up, and you inject silane. He took the very same machine, and he said, I'm not going to modify the machine, except that instead of putting the wafers of solar cells into it, I'm going to put our reactor with the graphite into it. So that means all of our equipment can be purchased from multiple suppliers, exists today when you go to factories that make solar cells. There is hundreds and hundreds of those stacks, and we use the same equipment. So we have no capex risk, and we can buy inexpensive machines that have been developed over the last 20 years by the industry. So at the end of the day, you can end up with very large volume production where the precursors are inexpensive, the yields are very high, and the capex is low. And that's how we end up with the cost structure that we do.
And it
And I
sounds
think that is the most important part, because all of the OEM we're working with, number one, they want to decrease the dollar per kilowatt hours of the cells. Number two, they want to increase energy density. Number three, they want to increase the charging speed. But it's in that order. And the number one, you cannot tell them, I'm going to promise you that. They want to understand and see it for their own eyes. And they want to understand, can you do it at scale? Because if you cannot do it for 3 or 4 million cars, it's useless.
and it sounds like your process, rather than requiring bigger machines to scale, you just buy, it's kind of modular. You just
One CVD stack is enough for 2 gigawatt hours of batteries.
nice. That's great. That puts it in perspective. And one of the questions I had while you were speaking was, does this require any special binder or electrolyte? Does it require any modifications on the cell end to make this work?
This is an excellent question again. So today, all of the testing that we're doing with our EV customers use the same binders, like 3% mixture of CMC and SBR, 1.5% of each, or even less.
Which are kind of like plastic and like styrene
Yeah.
butyrate or something like that. Yeah.
Yeah, and that's being used today in all EV cells. And it's mixed with water solvent. And then they can use Super P if they want to use a little bit of conductive additive. They can use commercial electrolyte and commercial, let's say, NMC 622 cathode or nickel-rich NCA cathode. They can use that in cylindrical 18650, or they can use that in prismatic or pouch cells. But here is the but. In addition to that, if they decide to go for dry electrode coating, then this will work very well with dry electrode coating, which saves them about $1 billion per gigafactory. And later on, our belief is that it will be usable also with solid-state electrolyte, although that's probably a decade away in terms of mass production. So this is not something that, is a one-time event. You can start by blending it with graphite so that you achieve the 500 to 600 milliamperes per gram in the anode that EV makers are targeting for 2025. And then in the subsequent years, between 2025 and 2030, you can increase the silicon percent by blending the Sinanode with less and less graphite as you modify the other piece of the stack, because everything has to go hand in hand, both the anode, the cathode, and the electrolyte. And so people are less interested in a big jump and more interested in a continuous improvement. So they want to invest in a technology that they can deploy in China, in Europe, in the United States, which allows them to use the existing supplier, the existing factories, but then has the improved manufacturing process or improved cathode or improved binders. They want to continue using that to push the envelope and get to higher silicon content over time. And so we're not trying to claim that you can start tomorrow morning with, let's say, 30% silicon and everything is hanky-dory. That's not the goal.
That's a good point. When you're dealing with cell manufacturing, you're dealing with so many sensitivities, safety issues. There's just so many variables involved that you don't want to change anything drastically. You want to try it out in the product and build confidence in it over time and potentially increase the amount that you're putting in.
That's exactly right. And when you talk to R&D folks in the EV cell makers or the OEM, they always like to try to push the envelope. When you talk to the purchasing folks or the production folks, they always try to minimize the number of changes in the cost. And so you kind of have to satisfy both audiences. You need, here is the thing that you can continue working on to match your product roadmap from a technology point of view. And this is something you can use now because you can use your existing suppliers, your existing factories, and rely with lower risk on the large volumes.
Now, I think it's a good time to wrap things up, to get a feel for what impact this has on the end product. What can we expect in terms of cycle life, energy density, charging speed, etc.?
So in terms of cycle life, so when we match the amount of silicon necessary to have the same reversible capacity as a silicon oxide graphite blend in the Tesla 3 or the Tesla Y, we need only 2.5%, which means that we can take 20% Sinanode and dilute that by blending with 7 parts graphite and 1 part 20% Sinanode. And that will have the same after formation reversible capacity, but it will cycle better. So when you go to 1400 cycle, 100% DOD, you will be higher than the blend with silicon oxide, okay? Now, as you increase that, we can get, for example, at 8 or 9 or 10% silicon, we can get initially in the range of, let's say, 500 to 600 milliamperes per gram in the anode, and cycle that in a full cell up to, let's say, 1,000 cycle, and still end up way higher at better than 80% capacity retention. And there is still a lot of work to be done in the terms of optimizing all of the EV cells. But what we have put together is a pilot program where each of our OEM customers can have their own pilot facility with their own CVT equipment and their own little team. And that team and that equipment is not used for anybody else. And then they can select which graphite to process, what silicon percent to do, and they have access to all the yield data, the quality data, the cost data, and it's their facility. And we are right now in the process of completing 2 new facilities for customers that will be operating by the end of the year.
Okay, so it's up to the manufacturer to determine how much silicon they put in their product. It's manufactured at one of their locations by using your equipment and oversight from your team, and then
we actually have leased buildings, so it's our location, and we operate it, but they pay us a fixed fee. But the difference is this: since we are a manufacturing step and not a material, they can choose different graphite, they can choose different silicon, etc. We have also optional process steps like carbon coating or doping that they may or may not want to use. And by doing something that is dedicated to them, the OEM can be sure that there is no leakage of know-how. And that's their own formulation, if you wish. And it's very important because A, they want to be able to differentiate from their competitors. And B, if you're going to be working between the material supplier and the EV cell maker to optimize things, there is always a risk of leakage of know-how. So we isolate that so that the equipment and the people only work for one OEM and nobody else. They have enough quantities, we can process, 2-3 megawatt per month. So they can, target 50 to 100 megawatts for the whole year, which is enough quantities to do a lot of EV optimization, where they can build enough cells to qualify the cells before they design that into a car. And we think that is basically 2022 will be the optimization duration for the EV cells, and 2023 will be the qualification, so that by early 2024, they can go in full production. And we are in parallel with that. We have retained a very large engineering firm that will build for us, it's currently in an early stage, the large-scale processing plant, which then will be able to process about 5,000 plus tons of graphite to add the silicon nanowires. And that will be ready in 2024 by the time they finish the qualification of the EV cells.
All right, so the energy density, cycle life, et cetera, will vary by manufacturer depending on how they've mixed it with their graphite anode, the characteristics of their graphite anode. So it's really going to be a range. Yeah.
Remember, they also have a product line, right? So at the high end, you may want to have a more expensive car with a more expensive battery that has more silicon and charge faster, and therefore you're going to use a different cathode. At the low end, you want to do a car that is at, let's say, $25,000 retail with a battery that is light enough and has enough energy that you can drive 300 miles, but where the cost has been reduced enough. And so you have to realize that in order to have a full product line, you're not going to use the same formulation at the top end and the bottom end of the product line. And that's why this facility, this dedicated pilot program, enables them to run different formulations. It's not just to optimize the cell, it's to optimize their product plans.
And I don't know if you can answer this. How is that going? Are they satisfied with the results so far? Is it meeting their performance criteria?
Yeah, so we have a 5-step process, and the first 2 or 3 steps are following. We first ship them full cell that we have coded ourselves with the anode and the cathode match, and we tell them this is what you should obtain in your lab, and then they duplicate that in their lab. Most of them have already completed that step because nobody believes your own data anyway. Then the second step, we ship the powder, and they do the rheology in a large slurry machine, and they do the coating on the large coating machine, and they look at the adhesion, they do uniformity, and so on. And some of them, but not all, have already done that step. And then the third is now we increase the amount of silicon to higher level. So we may be going from a nanode mix where the blend has, let's say, 430 or 450 milliamperes per gram, and we go to 500, 550, 600. And some of them have already done 2,000 cycles at, let's say, 550 or 600, and they don't satisfy. And now go to the next level. Now they say we're going to add various types of conductive additive. We're going to optimize the electrode design and the spec design, and that's beginning now. And then the next step will be to produce large enough quantities to provide enough material for enough EV cell to do qualification, and that's what will happen next year.
Do you have any plans to go public with the company?
Well, we have been fortunate because when we started this, I knew that this would take time because Yimin, our CTO, told me, Vincent, I can do all of the above, but you need to leave me alone and it's going to take some time. So we work with large customers and we collected revenues, tens of millions of dollars over the last few years. But we had a group of investors, 3 of which are multi-billionaires. And so we did not go and do a bunch of press release and raise a lot of venture capital, which, created its own problem. And what we were able to do is to basically, focus on the task at hand, remain very thrifty, and always say, you cannot make a baby in a month by having 9 women. And it's the same is true. You cannot make good software by having 10,000 software engineers. And the same is true about, electrochemistry. You're not going to go faster by having 200 electrochemists. As a matter of fact, you're going to make things worse. And so now that we are at the next stage, we are inviting some of the OEM we're working with to invest in the manufacturing plant so that they can really invest in 1D for the purpose of having a strategic investor that has a vested interest and is financially aligned with the production. But that was not necessary for the early phase where we financed it ourselves. Now, going public as its own, everybody's talking about SPACs, etc. The problem is that most of our customers are pretty tight-lipped with extremely strict NDAs, and I'm not sure that that's necessarily compatible with a public offering. So we may actually stay private, but we will, in due time, announce strategic investment from OEMs.
Okay. I think that's a good place to end it. I really appreciate your time today. It was It was entertaining, interesting. I got a lot out of it. So thanks for your time.
Thank you very much. I really appreciate your questions.
Cheers.
Bye-bye.